Page 10, number 45. ABCD is dilated by a scale factor of 5/2 and transforms into HIJK, which is not currently pictured. Identify the components of HIJK below. Okay, so when we dilate, what we do is we multiply. We multiply all of our lengths by the scale factor that's given to us. Now, I want to go ahead and draw HIJK so I can visualize this, and then we'll talk about the lengths and the angles and so on and so forth. I'm going to try my handy dandy tool, and if I am multiplying by 5/2 as a decimal, 5 divided by 2 is 2.5. So if I'm going to be multiplying by a scale factor larger than 1, my figure is going to get larger. It's going to get 2.5 times larger. So I'm going to draw my figure HIJK to be, 2.5 times larger. Something that looks larger at least. So let's go ahead and try. Awesome. Okay, so this figure is HIJK. Now we need to label it appropriately. They listed H first, which means that it matches up with A. A will turn into H. So A is on the bottom left corner. So I'm going to label H on the bottom left. B matches up with I. B is on the top left. So I'm going to put I here. And I'm going to keep going in that direction. This is J and this is K. Now, I need to solve for HI and I need to solve for JK. So let's start with HI. HI, which is right here, used to be AB before it was dilated. So what we're going to do is we're going to take a look at whatever lengths we need to figure out. We're going to multiply the old lengths by 2.5 or 5/2. And we're going to get to our new lengths. So let's start with the 11. 11 gets multiplied by 2.5 to become HI. So let's go ahead and write HI 11 times 2.5 equals, and your calculator, 2.5 times 11 is 27.5. So 27.5, and doesn't give me any units, so 27.5. That's my first answer. Next, I want to figure out JK. JK used to be CD. So I'm going to multiply the length of 4 by the scale factor 2.5 to figure out what CD is going to become. Now, 2.5 times 4 gives me 10. So my new length for JK is 10. So I'm going to put 10. Lastly, they're asking me for the measure of angle H. Now, angle H used to be angle A. What does not change as figures grow and shrink is the angles. Angles never dilate. Don't ever multiply an angle by some number. Don't do it. They stay the same. So angle H is going to be 105. Angle D and angle K are congruent, so K will be 120. Angle J matches up with angle C. Those are corresponding. So angle J is going to be 90. And lastly, angle B is going to be 45. This way, all 4 angles can still add up to 360, which is what any quadrilateral should have the interior angles sum up to be. So HIJK will add up to 360, and so will ABCD. If they didn't, well, then all of our rules about sum of interior angles just wouldn't make sense anymore. So going back to the question, the measure of angle H is the same as what it was before, which was angle A, 105 degrees. Okay, let's move on. Number 46. A rectangle has lengths of 10 and 14. A similar rectangle might have side lengths of, select all that apply. Now, similar shapes have consistent ratios for their sides. So what we want to do is we want to check that the ratios are going to stay consistent with the new side lengths. So for example, 10 is the shorter of the two sides between 10 and 14. It should match with 11 and create some type of scale factor. It should be the same scale factor as when you match 14, which is the longer side, with the longer side from your choice. So let's take a look. 10 and 11 should give me the same ratio as 14 and 14 if the two rectangles are similar. Now 10 over 11 can't be simplified. 14 over 14, well, that's just 1. So 10 over 11 should equal 1, but that doesn't make sense. That's not a consistent ratio. So no to the first choice. Let's take a look at our second choice. So we have 10, which is our shorter side, matching up with 15. And then we have the 14 matching up with the longer side of 21. 10 over 15 can be simplified if you divide by 5. So we're going to get 2 over 3. 14 and 21 can be divided by 7, and you get 2 over 3. Oh, it's the same ratio. That's exactly what I want. So choice 2 is correct. Those two rectangles will be similar because their sides are proportional. They have consistent scale factors. Okay, next choice. We have 10 matching up with our shorter side of 9 and 14 matching up with 18. 10 over 9 can't be simplified. 14 over 18 can. If you divide by 2, we have 10 over 9 and we have 7 over 9. Well, those aren't equal. So no, these will not be similar rectangles. Lastly, 16 and 21. Okay, 10 matches up with 16. Those are the shorter sides. And 14 matches up with 20. Those are the longer sides. Let's simplify. 10 and 16 can be divided by 2. So 5 over 8. 14 and 20 can be divided by 2. So we have 7 over 10. Those are not equal. So again, no to the last choice. We only have one correct choice here. 15 and 21 is the rectangle that matches up to the original rectangle with lengths of 10 and 14. And those will be similar. 47. The square pyramid pictured has a volume of 1,412.8 square units. Let's fix this. It should not say square. It should say cubic units. Cubic. That's an error. So the square pyramid pictured has a volume of 1,412.8 cubic units. Find the height of the pyramid to the nearest hundredth. Height. Okay, so the height, I like to draw it to the center. Needs to be perpendicular. I'm looking for that height. Now, they gave me volume, and they want me to find the height. That must mean I have to work backwards. Now, since this is a pyramid, a square pyramid, but a pyramid, we're going to write down our volume formula with a 1/3. So let's go ahead and get started. We're going to write V equals 1/3 big B H. That's a generic formula for anything with a big point at the top. Now, the height is definitely missing, so I can't plug anything in for this. However, I can start plugging things in other places. I can't forget that big B does not mean a number. It's hiding an area formula. It's hiding the area for your base shape. Now, since I said this is a square pyramid, that means our base is a square. So to find the area of this base, I'm going to be doing length times width. So I'm going to replace big B with length times width. And I'm going to bring down the H. Now, length and width are going to be the same because it's a square. So I'm going to put the 12 here as well. And I'm going to start plugging things in. So I have the volume They told me it's 1,412.8. So I'm going to plug in 1,412.8 equals 1/3. Length and width for your square are 12 and 12. And your height, well, that's what you're trying to solve for. So let's simplify this a little bit further. Let's go ahead and multiply all of this on the right hand side. So I'm going to bring down the 1,412.8. And now let's multiply. 12 times 12 equals, divided by 3 equals 48H. Last step, let's divide both sides by 48. So back to your calculator, 1,412.8 divided by 48 equals 29.43 repeating equals H. They want you to round to the nearest hundredth, so we're going to write 29.43 units, because it didn't specify centimeters or anything like that, just regular old units. Okay, let's keep it moving. Number 48. Two polygons are similar with a scale factor of 2 to 5. The area of the smaller polygon is 60 inches squared. What is the area of the larger polygon? So this is our ask. Now, I want to go ahead and draw a quick little visual. I'm going to make our two polygons triangles. And I'm going to go ahead and write out our scale factor, 2 to 5. Now remember, this is a scale factor for side lengths and for perimeters, but not for areas. They start telling us about the area of the different shapes. The smaller one, they said, is 60 inches squared. So I'm going to write down area equals 60 inches squared under our smaller polygon. They want you to find the area of the larger polygon, which I'll call X. Now, the way that we solve most similarity problems is through proportions. So I want to set up a proportion. However, I can't use 2 to 5 as my scale factor because that scale factor is not used for areas. For areas, I have to square that scale factor. Because remember, the inches are squared. The units are squared. So I have to square my scale factor. Now I can set up my proportion. So I'm going to do 2 squared over 5 squared equals 60 over X. Simplify the 2 squared and the 5 squared. So 4 over 25 equals 60 over X. Now let's cross multiply. 4 times X is 4X. 25 times 60. Let's go to my calculator. 1,500. Divide both sides by 4. X equals 375. And remember, that's area. So it's 375 inches squared for the polygon. I don't really know anything about this polygon, but I was still able to figure out that the area was 375 by using the appropriate scale factor for area. So my final answer, go ahead and write it in, 375 inches squared. Okay, let's keep going. Number 49. The following information is from the 2017 census. Which city has the greatest population density? Population density is found by doing a quick formula. I'll call it pop density. You're going to divide the population by the area of land that they occupy. So population divided by area of land. You're just going to use your calculator here. And for each one of these cities, well, actually, they're not cities. They're states. So this should probably say states. So for each one of these states, you're going to go ahead and figure out the population density and see which one has the largest, the greatest population density. All right, let's get started. These are pretty big numbers. 18,801,310 divided by area of 53,927. We get approximately 348. So 348. Let's actually change it to 349. 349. I'm going to round to the nearest whole number here. Next one, North Carolina. 9,535,483 divided by 48,711. About 195. Okay. So far Florida is beating. Let me zoom in so it's easier to write. Next, let's go to Georgia. 9,687,653 divided by 57,906 square miles. About 167. And lastly, Texas. 25,145,561 divided by 261,797. I was going to say it's a lot of people, but they also have the most land. So 96, they have the fewest people per square mile. Okay, so of our 4 different states, Florida has the greatest population density with close to 349 people per square mile. Okay, so that's our answer, Florida. Number 50. The areas of two similar, again, similarity, two similar polygons are in the ratio 25 to 81. Find the ratio of the corresponding sides. Okay, so they're asking you for the simple ratio of sides and perimeters. But what they gave us was a ratio, but not for the sides. It was for the areas. So if you recall, when we have ratios for areas, it's our regular scale factor, or our regular ratio for the sides, squared. So to get back to the regular ratio of just A to B, sometimes these circles aren't right. Okay, A to B, we would have to square root A squared and B squared, and that would get us back to AB. So we are given 25 to 81 as the ratio of the areas. Remember, that is the regular ratio squared. So to get back to the regular ratio for the sides, we're going to have to square root. So to square root 25 and 81, we're going to get back to square root of 25, which is 5, square root of 81, which is 9. So 5 to 9 ratio for just the sides and for the perimeters. 25 to 81 is the ratio for the areas. And then if you really wanted to follow up real quick, if we wanted our volume ratio, remember you have to cube everything. So 5 to the third power, 9 to the third power. So 5 to the third power is going to be 125. 9 to the third power, well, I think I didn't check that one. 81 times 81 times 81 equals, let me try it one more time. 81 times 81 times, not 81, 9 times 9 times 9, 729. Okay, so this would be our volume scale factor, or our volume ratio. But our final answer for the regular side ratio is 5 to 9. I had to undo the fact that the ratio 25 to 81 was already squared because it was the ratio of the areas. So final answer, 5 to 9. And we are done with page 10.